In the previous lecture, we have introduced and discussed some properties of the orthogonality in the inner product spaces. So let's keep going on with this topic. And the very first thing we discuss in this lecture is a distance from a point to a set. Before we go to the main theorem, let me briefly recap the notion of a convex set. So if we have a set A in a linear space, is said to be convex if for any xy from A, for any two elements, and for any scalar real number between 0 and 1, we have that this linear combination belongs to A as well. Well, this linear combination, when lambda running from 0 to 1, is nothing but an interval between x and y. So what this definition tells us that a set is convex if we take any 2 points from this set and the interval between these 2 points belongs to the set. Or equivalently, this can be stated as the midpoint belongs to the set. So these two are equivalent. Let me state a theorem about the distance to a set. Let A be a non-empty convex closed subset of an inner product space. Then, if we take any point from our space H, there exists a unique point y from A such that the norm of the difference x and y equals to a distance from a point x to the set A. Or we can write the distance as an infimum. So we take the infimum, we take any point from the set A and compute the distance from x to A and take the infimum. So the distance from a point to a set is the smallest distance in the sense of infimum. And we claim that this distance always attained. So there is always a point y such that this distance equals to the distance between x and y. So first of all, let us fix a point x and let gamma to be the distance from x to A. Let me remark that gamma is well defined, since the set of numbers is bounded below then gamma is well defined. Let me now use the definition of infimum to say that for every natural number n, there exists a n from A such that the norm of x minus a n squared. Well, by definition, we know that this is greater than or equal to gamma. And again, by definition of the infimum, it is less than gamma squared plus 1 on n. What I want to do now is to show that this sequence an is a Cauchy sequence. And, okay, yeah, and over here I have to assume that this space is Hilbert. Of a Hilbert space. So now the plan is to show that the sequence an is a Cauchy sequence. So using the completeness of the space, we can claim that it converges, and we will claim that the limit of this sequence an is the point y which we want. Let me write a parallelogram law, parallelogram identity for two elements, for element p minus an and p. It's x minus an, and x minus am. So in the parallelogram identity, in the first norm, we have the sum of these two elements. Plus, in the second norm, we have the difference of them. And it equals to twice the norm of the first one plus two norms of the second element. So this is just the parallelogram identity. Okay, let's now simplify it a little bit. So, what we have here is 2x minus an plus am plus the norm of an minus am. I wrote the parallelogram law in almost correct way. I forgot squares everywhere. Should be squares here. And here, and here, and there. And then I will use that estimate to get that it is strictly less than 2 gamma squared minus 1 on n plus 2 gamma squared minus 1 on n. The aim is to prove that the sequence an is Cauchy. So this is the term which we wanted, and we want to show that this one tends to 0. So these are kind of nice. These terms look problematic. So over here we have a sum of two elements from A. Since we assume that A is convex, then the midpoint between these two also in A. And so what we have here is the norm of the difference of x and some point from A. By definition of the infimum, we can estimate it from below by 4 gamma squared. And now, having this estimate, I will bring this norm to the right hand side. Well, 2 gamma squared plus 2 on n, 2 gamma squared plus 2 on m. Now I will bring this norm to the left and estimate it by this one. So it will be minus 4 gamma squared, which is 2 on n plus 2 on m, which tends to 0 as n and m tends to infinity. So the sequence which we introduced there is Cauchy. Since our space is Hilbert, so complete, then this sequence converges. Also, since A is closed and the sequence AN belongs to A, this little a belongs to the set A. Well, now the aim is to show that this point A is nothing but the point Y we're looking for. We have that gamma squared less than or equal to the limit of x minus an when n tends to infinity. Well, this inequality holds for any n, so we can take limit. And yes, since we have square here, let's write the square here as well. Now, taking the limit, we obtain that this equals to x minus a squared. I will write it now again as a limit x minus an squared and to infinity. Then estimate it using the second inequality as gamma squared minus 1 on n. Which is gamma squared. So we proved that there exists a point at which the distance is attained. Let us now show that this point is unique. Okay, so let us suppose that there are 2 points at which the distance is attained. I will write again the parallelogram law for elements x minus y and x minus a and x minus y. Doing pretty much the same thing, so I will keep this norm on the left. For this one, we have that it is less than or equal to 2 gamma, just equal 2 gamma squared plus 2 gamma squared minus and now in a similar fashion I will estimate this term as 4 gamma squared. Which is 0, and well, as a norm it is greater than or equal to 0. So the norm of a minus y is 0, so the element is 0 itself. Couple of remarks on convexity. So why did we introduce this notion of convexity? We used it for the first time in the course. So why is it so special? So remark. If A is not convex and H is finite dimensional, then this point Y might not be unique. Well, it's not very difficult to construct an example. So in R2, let's consider a sphere in R2 centered at 0. This set is not convex, and the distance from 0 to the sphere, is attained at every point of the sphere. So this point is essentially not unique. Well, if the set A is non-convex and the space is finite, the space is infinite dimensional, then this point Y might not exist at all. Okay. So in the previous lecture, we discussed the case when two vectors orthogonal to each other. Now let us consider the bunch of vectors which are orthogonal to the whole set. Or rather for a subset, H is any in a product space. We call a set which we will denote by A orthogonal, which consists of all vectors from H such that xa equal to 0 for any point A from A. So it consists of all vectors which are orthogonal to any vector from the point A. We call this set the orthogonal complement. Let me write down a simple example and then list, well, also simple properties of orthogonal complement. For the example, let us consider R3, and let A be the set of all points of the form x, y, 0. Then the orthogonal complement of A is the set of all points with the first two coordinates being 0. So if, well, A is the x, y plane, it's 0. And a complement is the z-axis. Now let me list the properties of orthogonal complement. Proposition. Let V, let's go for H, be an inner product space. And let A be a subset. 0 belongs to orthogonal complement of A. As a consequence of this one, so if 0 belongs to A, then A and A complement, orthogonal complement, intersect by 0. Otherwise, they do not intersect. The orthogonal complement of a zero set is H, and the orthogonal complement of H is 0. So if A is a subset of B, then if A is non-empty and open, then its complement is 0. A complement is always a closed subset, a closed subspace. A is a subset of its double orthogonal complement. Let H be a Hilbert space and let A be a subset. Then, first, if A is closed, then A equals to its double complement. In general, a double complement equals to the closure of A. And the final property that a subset is dense in this space if and only if its orthogonal complement is 0. Let us now introduce the notion of orthogonal representation. Let G be a closed subspace of an inner product space H. If X can be written in the form Y plus Z with little y belongs to, let's go for y over here instead of G. Yeah, let it be y. Little y belongs to the capital Y, and Z belongs to Y complement, orthogonal complement. Then we say that this form is an orthogonal decomposition. Well, in the next theorem, we will prove that in the case when the inner product space is complete, the decomposition, the orthogonal decomposition always exists and it is unique. Let Y be a closed subspace of a Hilbert space. And let X be an element from H. Then there exists unique Y from Y and Z from Y complement such that X equals to Y plus Z. Let's prove this. Let us fix X from H and let Y be the point where the distance from X to Y is attained. By the previous theorem we know that such point exists and it is unique. And we claim that this little y is exactly the y we need. So what we need to show is that x minus y belongs to y orthogonal complement. Or in other words, that x minus y is orthogonal to any element of y. So let us take any point from a subset y. Due to the choice of little y, we can say that for every scalar lambda, we have that x minus squared is greater than x minus y squared. So the distance from x to any other points of y cannot be less. So let me flip it over and expand this one, which is equal to in terms of the inner product, and now I will expand it keeping x minus y together. Now I will cancel this term and bring these two terms to the left hand side. And now we will choose a convenient value of alpha. So in particular, I want to choose t between 0 and 1 and set alpha to be t if x minus y w is 0 and t times this one if it's not. Let me now take this value of alpha and substitute it into our inequality. I will start with the first case, with this one, and then explain why the second one works as well. So when I take this alpha and substitute it over there, I have quite a lot of, well, this term and this term cancels. So I get t plus, oh, well, it's the same term. That's just 2t less than or equal to t squared norm w squared. And well, if this expression is 0, then this estimate is also true. Let me now cancel t. So this estimate holds for any t, well, between 0 and 1. So in particular, we can take a limit when t goes to 0, yeah, and it still will be correct. Which means that the inner product inside equals to 0. But what do we know about w? The only thing we know about it is that it is an element of y and nothing else. So it is a generic element of y. So we proved that x minus y is orthogonal to any element of the subspace big Y, which means that it belongs to orthogonal complement. So by proving this, we established a orthogonal decomposition. But we also need to prove that this orthogonal decomposition is unique. Well, you might say that for this y, we've taken a unique point where the distance is attained. So y is the point where the distance from x to the set y is attained. And by the previous theorem, it is unique. But it doesn't mean that the decomposition is unique. So for instance, this decomposition into y plus z might hold for some other y. So we still need to prove uniqueness. But that's not very difficult. So as usual in the proof of uniqueness, let us suppose that there are two decompositions and prove that they coincide. Then y1 plus z1 equals to y2 plus z2. Or y1 minus y2 equals to z2 minus z1. But what do we have here? y1, y2 are elements of y. So y1 minus y2 is also an element of y. But on the right, we have an element of y complement. So a subspace and its orthogonal complement can only, if they do intersect, they only intersect by 0. Well, which proves that y1 equals to y2, z1 equals to z2, and so the decomposition is unique. Well, this uniqueness is a very nice property. In particular, it allows us to define a projection of an element x onto a subspace y. Let y be a closed subspace of a Hilbert space H. Just a mapping Py from H to y given by Py of x equals to y, where x equals to y plus z, the orthogonal decomposition. So we call this mapping an orthogonal projection or a projection. Let me state a few simple properties of this orthogonal projection. Let P, well, y be an orthogonal projection. Then, first, P is linear. Well, in the sense that P of alpha x1 beta x2 equals to alpha P of x1 plus beta P of x2. The norm of Py of x cannot be greater than the norm of x itself. This follows from the triangle inequality and the orthogonal decomposition, of course. What happens if we apply this projection twice? So we make a composition. Well, p squared, but what is it?
P1.
It's just p itself.
P1.
Yep. So this property of mapping called idempotency. One more property is that the image of py is, well, of course, y. And what is the kernel? Where should be an element such that p of y be 0 in the complement? So we have just proved that if y is a closed subspace, then we can write any element of our Hilbert space as a unique combination of an element from y and from its orthogonal complement. So in this case, we say that a space is written as a direct sum. X is a direct sum of y and z. We will write it x equals to y direct sum z. Well, as an immediate corollary of the previous result, we say that any Hilbert space can be written as a direct sum of its closed subspace and the orthogonal complement. Well, we have proved that any Hilbert space can be written as a direct sum of any two spaces. They are of quite special term, of a quite special form. But what about the general definition? The definition stated in general linear spaces. So can we get this result, the result of this type, outside of the inner product spaces? Let's have a look at the example. C0 subset of C subset subspace of L infinity. So this is the space of all bounded sequences. This is a subspace of all convergent sequences. And this is the subspace of all sequences converging to 0. So we have seen these spaces before. And well, this infinity stays for the uniform norm. We have discussed already that a space of sequences with this norm is not inner product space, because the parallelogram law is not satisfied here. So it's not a Hilbert space. But anyway, can we write C as a direct sum of C0 and something else? Let's try it. So for x in C, there exists well, let's go for real sequences. A real number such that xn minus a converging to 0. Well, this a is nothing but the limit of the sequence. So in particular, a sequence xn minus a belongs to C0. Well, I wrote twice pretty much the same stuff. So every element from C can be written as an element from C0 plus a constant sequence. Z with Z equals to X n minus A. So, well, over here A is a number, but over here A is a constant sequence with every term equals to A. Okay, so we have managed to find a unique representation of X, and in this unique representation, the second term is from C0. Where is the first term from? So the first term in this decomposition is always a constant sequence. But a constant sequence is determined by a single number, by a single real number. So the space of all constant sequences is isomorphic. Well, it's not even isomorphic, it's isometrically isomorphic to real numbers. Then C equals to a direct sum of real numbers and C0. So we agreed several lectures ago that if the spaces are isometrically isomorphic, we think of them as being the same. So sometimes it is possible to write a space as a direct sum of two other spaces, even without the inner product. But is it always true? Well, of course it's not. L infinity is not a direct sum of C0 and any other space.